So welcome back. Thank you for coming back so punctually from the coffee break. We're running a little bit behind schedule, but we'll stick to the current schedule plus 10 minutes. So it's my pleasure to introduce my colleague, Kent Wallace, who's going to tell us about dual-purpose focal plane masks for simultaneous wavefront sensing and high-contrast imaging.
Thank you, Gary. Thank you all for attending, and I really mean that. I think we're maybe suffering from a little bit of conference fatigue. I realize it's a Friday afternoon after a long, exciting week with a lot of talks. I feel like I'm also competing with the curling competition at the Winter Olympics. So I'll try to see if I can keep it somewhat exciting. But there's a lot of material to go through. I'm going to have to hustle, so I apologize in advance, but let's go. Thanks to my team. These guys are exceptional. They each have contributed in very unique and special ways. I value them immensely, and I couldn't have done this work without them, so thank you, guys. This is the image that we have to keep in our head. We all want to see this. We have to work for this. We have to work very hard for this. But this is what we're after. This graph has got a lot of traction this week, so thank you, Vanessa and company, for generating this. Let's ask ourselves where we are with regards to being able to image such exoplanet systems. My experience was primarily from ground-based instruments, and for GPI, for instance, we needed wavefront stability on the order of a nanometer. The contrast that we're trying to achieve with HWO is 4 orders of magnitude greater. And that means that the wavefront stability needs to be 100 times better. That means we're shooting for 10 picometer wavefront stability. Now, keep in mind that the diameter of a hydrogen atom is 150 picometers. So we're trying to get stability at 1/10 of a diameter of a hydrogen atom. If you're bored, you can look up what the nucleus of a hydrogen atom is, because I'll be touching upon that. Turns out this contrast level is hard, but I think we kind of sense that. Well, how do we approach this problem? What we do is we want to create and maintain the high contrast condition, and this is our very incredibly expensive design for such an observatory, a high contrast observatory. On the left is a telescope, in the middle is the DM relay, and then on the right is the chronographic system. And so the trick is to first establish the high contrast condition and then maintain the high contrast condition. Now, I claim that the high contrast condition happens right here. Now, we can argue about this after my talk, but that's where we are going to establish the high contrast, and it's where we're going to measure it with our wavefront sensor. And we're going to maintain that contrast by feeding back the error signal from the wavefront sensor to our DM relay. Let's take a closer look at that focal plane mask. This is our concept for actually implementing that. There's a lot of things going on in this diagram. I'm going to work from the back of the substrate to the front. We want to make sure that the back AR surface is as good as possible. We want to make sure that our substrate is as pure as possible. It has to be thick enough and wedged enough to mitigate against ghost. It has to have 0 striations and bubbles, inclusions. And then we also want to make sure that this dielectric is designed in such a way that we have high transmission for the chronographic light. The chronographic light goes straight through. And in reflection, we have to have high reflectivity at the shorter wavelengths. And then we also have to have a chronographic stop, and we have to have a Zernike wavefront sensor in the middle. And this is what constitutes our dual-purpose focal plane mask. I'll go into more detail about some of the aspects of this. So the first question is, what's a Zernike wavefront sensor? Well, it's a system that has this. It has a very special focal plane that has an etched dimple at the middle, and you center your PSF on that dimple. And that provides a phase shift to the core of the PSF. As that light then propagates from the focal plane, the beam expands, and in the collimated space, that low-order light combines with the high-order light, and it produces an interference fringe. It's on axis, and it is what optical people call a common mode white light interferometer. And you think, is that it? And yeah, that's it. But it turns out it got Mr. Zernike his Nobel Prize. It wasn't because of his polynomials, I can tell you that. Okay, so what does this Zernike wavefront sensor do? Well, this is the response of the intensity in the pupil plane of the Zernike detector for the phase aberration that is in the pupil plane. So this is a phase aberration in the pupil plane. Let me walk through the terms here very quickly. This is the intensity in the input pupil if there were no Zernike dimple at the focal plane. This little phase shift here is due to the Zernike mass, that little dimple depth. B is the magnitude of the electric field from the reference beam. This is, again, the pupil electric field, the reference electric field. And then this little term here is the phase that's resulting from that reference beam. Complicated expression. Let's take a closer look. If you have yourself an innie, if you're an innie, then the response of the Zernike is as shown here. It's not centered at 0, because when you have 0 phase error in the pupil plane, you have a little response from the reference beam that illuminates. So that's the response. It curves over when you exceed one wavelength of phase excursion. Okay, so what happens is there's a degeneracy, and you're not sure which phase is associated with which intensity. So you've got to be a little bit careful on how this is interpreted. If you have an Audi, it turns out you can have a different signal. It's also phase shifted, same brightness with 0 phase errors in the pupil. And it gives a similar response, but it also wraps, and you have a degeneracy in the intensity of your signal. This is what the response looks like now when you have a much smaller input phase error, but you can still see that there are degeneracies that you have in the brightness. So this intensity can be associated with 2 different phases. Ideally, I would say naively, I want to have an innie and an outie at the same time, because that would allow me to unambiguously determine what my phase is. And then this is where we want to be able to look at picometer level phase errors. This is 50 picometers here on this axis. We have to look at the signal and see that we're really just measuring very small changes in the intensity of our light. So for 50 picometers, I believe it was like a part in 10,000, something like that. So it's a very small change in the intensity, but that's all it is. So the question isn't like, what is the signal? The question is, how many photons do you need to be able to measure a part in 10,000 if you want to measure 50 picometers? And that noise is associated with all the noise sources in the system. The detector noise, the photon noise. Typically, it always comes down to just get more photons. Okay. So our custom dichroic has to be reflective in the blue. It has to be transmissive, very transmissive in the science band. And we have to make sure that the phase is very well defined, so that it's the phase corresponds to the depth in the coding where the reflection occurs. And yeah, there's some sort of weird depth that's associated with where a coding. We keep our coding thin. This is only 14 layers, so that the depth is small, so that the phase upon reflection is well understood and very small. We characterized it with a precision white light interferometer. Dan Shanks helped build this instrument, and it allows us to characterize many aspects of the focal plane masks. Okay, here's the final mask. Here's what it looks like in a picture. We can see that to our eye it looks blue because it's a mirror in the shorter wavelengths. If we could look only in red light, this would look like it's almost not there, because it's very transmissive. The AR coding on the backside is very good. At the very center, however, there is this mask, what we call the wedding cake. So we have the aluminum disc that is the chronographic stop, and then the Zernike dimple on top of that. The depths of these depositions are very finely controlled. Ask yourself, how transmissive is aluminum when it's 57 nanometers thick? Anyway, this design process is very detailed, but it was the result of a lot of hard work. We put it in the test bed, and how did we do? How did we do? Well, it goes in this focal plane element right here. We take this light, shove it into the wavefront sensing camera. The rest of the light goes to the science camera. The first thing we wanted to do was make sure that we did not destroy the ability to suppress starlight. And so this is what we were able to do. We measured the contrast in 5 different spectral bands, 2% each, so a total of 10%. And we got contrast levels that are consistent with the best levels for other coronagraphs. So we're very happy about that. This super fancy focal plane mask turns out did not destroy the coronagraph. Yay. How well did we do with regards to wavefront sensing? This gets to be difficult to explain in a short amount of time, but let me give it a shot. We poked up the DM in a grid pattern up and down, and then we took differences of those up and down intensity signals, and then we averaged. And we took a lot of averages, but what we can see is that ultimately we were able to see on top, so this poke pattern is only 1 bit of the drive electronics for the DM. So that is equivalent to a 15 picometer poke. What's the level of the gray and around that poke? Well, it's about 0.7 picometers, or I would like to say 700 femtometers. The diameter of a hydrogen nucleus is around 150 femtometers. So now we are getting to within spitting distance of nuclear distances. That's kind of weird to think about. Okay, well, great. Can we put all these things together in order to do what we said we wanted to do? Sense the wavefront in reflection from the chronographic mask while also performing starlight suppression. Again, this graph has a lot going on, and I don't have a lot of time to talk about it, so I apologize for that. But what I'm going to show is this, is that on this image on the left-hand side is the injected disturbance. Once that disturbance is injected, we give ourselves 10 seconds to measure it, and then we correct it, and then we apply it, and then we look at the difference. So this is the intensity before we close the loop. This is the image in the focal plane after we close the loop. And then there are several instances of this for each chunk of time. We have a new random instantiation with each tick of the clock. Okay? So let's see if we can measure this. So again, the raw contrast, if you will, is at the 10 to the minus 8 level, and the corrected and controlled is at the 10 to the minus 9 level. So we were able to roughly improve the contrast by wavefront sensing and control during a science observation by a factor of 10. Great. Good. So let me say, there's a lot going on here, and let me just go over briefly, because this is not all. It turns out you can use the information that you get from the wavefront sensor to also estimate what's happening in the science focal plane, and then form an estimate of what your contrast would otherwise be. And using that extra information, you can also improve the contrast. So there's a lot of groups that are working on this. Emil Poor, for instance, I'm kind of feeling his absence. He is not able to make it, but he's doing similar work as well. I also want to say you can add on top of the wedding cake metasurfaces. We've talked about metasurfaces, sub-wavelength features that allow us to control the phase and amplitude of electric field at very fine spatial scales. This is the thing that gives me the innie and the outie simultaneously. So in one direction, I have a one polarization state. I have one phase delay. In the orthogonal polarization, I have a radically different phase delay. And taken together, those two allow us to do exactly what we wanted to do. Have a difference in intensity signal for the two different polarization states to extend our dynamic range. So what are the takeaway messages? Key takeaways. Number one, the dual-purpose focal plane mask has demonstrated the ability to suppress starlight while measuring and maintaining wavefront stability with a minimum of non-common path optical errors. Metasurface integration into the phase dimple extends the dynamic range. That's great. The active wavefront sensing and control capability ensures that the requisite starlight suppression while also relaxing, this is key, relaxing the stability requirement of the observatory. That's a huge one. Let's go, HWO. Let's go. Let's go. One last takeaway. I'm sorry I'm running over. Today's my daughter's birthday, so that's great. It turns out it's also the birthday of GPI, because the proposal was due the day that she was born. So it's good. Thank you.
Okay, we have time for, I believe, one quick question. Dimitri, you want to take it?
Awesome talk. So I will paraphrase the Mandalorian. This is the way. Are we done? Is there any way we can actually push this concept to higher throughput? Because my understanding is that it's still the one weakness of this chronograph architecture. Can we extend this to other chronograph concepts that have slightly higher throughput or much higher throughput?
Yeah, that's a great question, Dimitri. Can this be modified or extended to work with other chronographs? So Tobias submitted a proposal where we actually proposed doing exactly that, using this kind of similar concept of using the rejected starlight. This time it's a combination of a little bit of light at the focal plane, but also light that's rejected from the Leo plane of the vortex, to be able to do this wavefront sensing and control. Also, we're just starting to look into making the Zernike mask more controllable. So if we can actually also measure the electric field amplitude in the pupil, as well as the phase, that would give us a lot of power. We're working on that too. So.
Let's thank Kent again.